Now, of course, you need to take care of maintaining the information that allows you to know where each file is. And you, in this case, is the operating system. But you need to do the same also to keep track of what portions of your disk are actually free if you have to store something new in one of these portions. So how do we know what portions of our file system are free? I'm going to show you two ways to go here. The first one is to use again a linked list in which you store basically the addresses of the blocks that are free, and you use one last address to point to the following block that contains the lists of blocks that are free, and so on and so forth. Okay, and this can be maintained on disk. It's similarly to how you allocate files. The only difference is that now you are filling it with addresses that are referring to blocks that are free rather than already used by some file. Or you can use a bitmap. So you can set a bit for each block from the first one to the last one. 1 means it is free, 0 means it is already taken, or the opposite depending on how you implement the system. But let's say the binary information tells you whether it is taken or not. Now, which one is better, as always, depends. If you have a small number of free blocks, the linked list might, for example, consume less because a bunch of blocks on the disk would already contain all the free addresses. On the other hand, if you have a lot of free addresses, the bitmap might consume less space, despite the fact that it takes always a fixed amount of space because you need 1 bit for each block, and the number of blocks is fixed, all the blocks you have in the disk. Again, be efficient in how you keep this. It's always more challenging than it looks, at least as based on how we discuss these things in the course. So let's say that you go for the linked list. And let's say that for efficiency, you only keep the first block that is containing free addresses of free blocks in memory, and the rest you keep on disk. And let's say that the idea is to do this because you want to get a better performance by interacting with the memory rather than the disk and consume less time. Sounds like a good idea, but you can still end up in some degenerate case. So here I'm just trying to make an example to show you that, as always, there are always trade-offs. It's complicated when you want to implement efficient solutions for these kind of problems. And what the example shows you here is that suppose that you have the block in memory that is almost full of free blocks. Okay, let's say there are only 2 remaining, and you compile a big program and you keep creating a lot of temporary files and deleting them and creating them and deleting them and so on. So every time you delete a file, you free space. You want to keep this free space in this list because you could use it later on. And so you store the free blocks here in these free ones. You exhaust this block, so you write it to disk and you create a new one, and then you keep adding the blocks that are free. But then you have to create a file and you need more or less the same number of blocks. So you start consuming the ones you have in memory. You only have a bunch of them. Then you exhaust the block and you need to read it back from the disk, and this the same block you just wrote. And if this is happening a lot of times in a cycle, in a small amount of time, you see that your desire to optimize the thing actually led to a solution that creates a lot of overhead and a lot of writes and reads from the disk and creation of space in memory, because you are just unlucky and you end up in one of these corner cases. Okay, it's just a small example to show you things that can happen that make this kind of designing a file system and other parts of the operating system too complicated.